this video, I want to talk about the topic of curvilinear motion. So curvilinear motion, as opposed to linear motion that we've been talking about so far, starts to introduce change in direction. So when we talk about a particle moving from one place to another, we can talk about how it changes in time. So as it gets from one point to the next, some time passes, and that happens slowly or quickly depending on velocity and acceleration and so forth. Curvilinear motion introduces change of direction, which can occur at the same time. So if we think about a particle traveling along a path, that path can be relatively arbitrarily designated. So I can have some random curved path, and my particle can travel from one point on that path to another point on that path. And it's constrained in this case to travel on the path in that we've defined what the path is that this particle is going to be traveling. Now, we want some way to kind of specify what's happening here, so I'm going to go ahead and draw a coordinate system. And in this case, I'm going to use an XY coordinate system. Again, for my example here, it's just kind of arbitrarily placed. And then to define what's happening with this particle, I'm going to say, well, there's a vector which I'll call R1, which is a position vector defining the location of that particle at some point in time. And then there's another vector, R2, which defines the location of this particle at some secondary point in time. Now, what happens in between those 2 points kind of depends on your perspective. One way that I can represent this, if I'm doing it in kind of a discrete fashion, I can say, well, at time 1 it's located here, at time 2 it's located up here, and there's a change between those two that occurs. And I'm going to call that change, in this case, delta R, as a vector quantity. So if I only knew what was happening at time 1 and time 2, like I had two snapshots of those points in time, I might only know this change delta R, meaning that that's all I've seen to occur. Now, of course, we can use this then mathematically to represent what's happening and get a relationship between all these positions. For example, if I look at these as vector quantities, I could say that R1 plus delta R is equal to R2, and that's just a vector addition that we can see graphically by looking at this. And of course, then I could define or rearrange this equation to define that delta R as the difference between position 1, position defined by R1, and position R2. And that, is maybe useful for me in some cases, depending on what I know about my particle and where it's been traveling. Now, another way to look at this is that if I knew more information about this path, or maybe I had more snapshots, more points in time, more data, I might know that my particle travels along this path that looks something like this. And I'm going to call this delta S, so change in some position. Sometimes we might look at this as an arc length, for example. So that can be useful, especially if I zoom in on a close enough, small enough change in position along this path. I can approximate delta S as a portion of a circular segment, a circular arc, and then that becomes mathematically useful to me in that I can start to define some things based on that. So suppose we do that. Let's get back to my original color here. Suppose I take and I zoom in on a portion of this. So I'm going to redraw a coordinate system, again, just kind of arbitrarily specified, and I'm going to draw a segment of my curve. I'm zoomed in on it now, and I'm going to say that over the segment of the curve, it's so small that I can approximate it as a nice circular arc, meaning that it's got a constant radius of curvature all the way across. Now, of course, my drawing doesn't look like that because it's not a very good drawing, but let's pretend that I can do that, which means that I'm going to take and dash a line in here, This line is in theory perpendicular to my curve at that point, and I'll do the same thing on this side. And wherever they intersect helps me define my radius of curvature, which I'm going to define with rho, or label rho. And there is also some angle theta. Now if I say that then the arc length of this segment is s, so the change in length around this curve at that point, well then I know from math or geometry or whatever form of math you like that s is equal to rho theta. And that's nice, that's useful, it's a simple equation. I could also zoom in on this and say that a small differential unit of s is equal to rho, which is just a constant, times a small differential unit of theta. So if I zoomed in very, very close, I might use differential units and sum them up, which forms the basis of an integral. I could also rewrite this then as d theta by ds is equal to 1 over rho. And that's nice. We'll come back to that in a little bit. So the other thing that I might be concerned about is what's happening to my particle in terms of velocity and acceleration. So let's go back again and come up with a curve on a coordinate system. And my particle is, let's do a better curve, just to be easier if we just do a kind of curve thing like this. My particle is traveling along at some point in time. It's got a position defined by r, and we know from how we define the motion of this particle that if I were no longer constraining this particle to this curved path, if I just kind of let it go from the path and it was traveling with some velocity, it would travel off in a straight line. Newton's laws tell us that. So in that case, we would know that it has a velocity at this point in time which is tangent to this curved path at this location. So we know the direction of that velocity vector, and we can draw that on here in this way. Now what we don't know necessarily is the direction of the acceleration vector. So we need to think about what acceleration is. If velocity is a vector, right, then acceleration is the rate of change of that velocity, right? And velocity, again, being a vector, is defined as having a magnitude, which we might call a speed, and a direction, so an orientation of that vector. Now, if acceleration means change in velocity or rate of change of velocity, then I could change my acceleration by doing one of two things. I could change the speed of my particle, or I could change the direction that it's traveling. And both of those things would define a change in acceleration or create a change in acceleration. So because I have those two things, without knowing more information other than just the geometry that I have shown on the screen, I can't fully define what my acceleration looks like. So as a result, my acceleration I'm just going to represent as kind of an arbitrary vector off in some direction. I can't say that it's tangent to the curve. I can't say that it's normal to the curve without knowing something about how the speed is changing, for example. So first, let's think about velocity a second. Velocity, we just got done describing as being tangent to the curve, and we also know that it is the rate of change of position. So just like we've done before, in 1D motion, we would define velocity as the rate of change of this vector quantity r. And We just got done describing how the velocity makes up or is made up of a speed and a direction. Speed specifically would be then the magnitude of that velocity, and we can represent that using this arc length that we defined above, and how that changes with respect to time, how the change in position along the path changes with respect to time. Now that doesn't contain directional information, it's only that arc position s. So we've got magnitude of the velocity vector representing speed, and we've got velocity being the time derivative of our position r. And I'm not going to get into actually carrying out those derivatives of these vectors. That's not particularly relevant and for anything that we need at the moment. Next, we have acceleration. And acceleration is equal, as we've described, to the rate of change of velocity. But now, because we have these two components of this, we need to split this out into two separate pieces. And I'm going to, for convenience, define them in tangential terms and normal direction terms. Now, when we talk about curvilinear motion, we could talk about things in a Cartesian coordinate system, using x and y and even z notation for three-dimensional. We could do that. That's sometimes useful. We can talk about it in terms of cylindrical coordinates, which again is another way to represent it and sometimes useful. I'm going to use, in this specific case, tangential and normal direction just because they're kind of useful for some scenarios, and we know their directions in a curvilinear problem like this. So I can go ahead and represent the components of my acceleration in those directions. So the tangential itself we can define as the rate of change of the magnitude of the velocity vector, so the rate of change in the speed, and I'm just going to write that down, what I just said. Change in speed. And we can define the normal direction using this equation. Again, magnitude of the velocity vector squared over rho. And this equation comes from the vector derivative that we would take of velocity in order to arrive at these two components. Again, the dynamics textbook would walk you through how to do that, but it's actually, to me, not terribly important. So we're just going to use this equation as that normal acceleration. And what this practically represents for us is the change in direction of our particle, the rate of change in the direction. So we have one component of acceleration representing rate of change of speed on the left in the tangential direction, and then we have a component representing rate of change of the direction of the velocity vector. So what I end up getting here, and I'm going to kind of run out of colors here, I'm noticing, what I'm going to get here then is a tangential acceleration, which is going to be in the tangential direction, which is coincident with my velocity vector, and a normal direction, which is perpendicular to the curve at that point, which represents my normal vector. And of course, I'm breaking down effectively into vector components, tangential and normal components, this acceleration vector that I've drawn here. So you can kind of see what's happening as this particle is moving along, and it has some speed, and that speed is changing. Say this is a car driving on a curvy road. that change in speed may be occurring because I'm accelerating, pressing the gas harder, or I'm braking. The normal direction of the acceleration is occurring because I'm turning the wheel, right? I'm following the roadway by turning the steering wheel, and as a result I achieve this normal direction acceleration, which represents that change in direction. Okay. Now I very briefly just want to mention a kind of useful and let's say common application of curvilinear motion in general, and that is projectile motion. It's kind of a special case, a little bit of a simplification in most cases. But again, because it's so common, it warrants a little bit of discussion. So projectile motion means that, let's define a ground plane here. I have some object. I'm going to give it some initial velocity at some orientation. And we know that if we do this, so imagine throwing a ball in the air, right? We know that if we do this, it's going to travel up, stall out, and come back to Earth, right? And if you've taken any classes where this has been discussed before, you'll know that it's going to follow this parabolic curve, and you have some idea of what that looks like. Now what we know at this point is that the only thing that's acting on this is the downward acceleration of gravity, g, and we know that that's constant, right? If there's nothing else happening, this is assuming not an accelerated system, so it's not like a rocket or something like that where there's acceleration being added, within the device or within the object itself. But it's like a baseball or a basketball being thrown in the air. It's subject to the acceleration downward of gravity, and in the horizontal direction, there's not really anything acting on it. It's given an initial velocity, but after that, nothing happens. So previously we talked about constant acceleration and constant velocity simplifications for motion. And what we can see here, I should probably define x and y. What we can see here is that y represents a constant acceleration condition, and x represents a constant velocity condition. So we can use those two things in order to understand what's happening with this ball or whatever it is at any point in time as it follows this curved path. And again, here I'm using a Cartesian coordinate system to kind of define what's going on, and it's useful in this example because my known states are in Cartesian directions. My constant acceleration is in a vertical direction, my constant velocity condition is in a horizontal direction. That doesn't mean I'd have to evaluate this problem or a problem like this using Cartesian coordinates, but it might be useful. I could represent it in normal and tangential components and make some adjustments with geometry and such. But this is a good place to start. So that's something that comes up a lot in various problems that we might look at, and it's kind of useful to look at that further. All right, thank you.